For the final talk of today, we have Vestislav Apostolov, who's going to tell us about the Calabi problem with generalized Kahler structures of symplectic time.
Thank you very much. It's of course a great honor to me to speak on this occasion to celebrate 50 years of Nigel Hitchin mathematics. And I will speak today about a joint project, a joint paper with Jeff Streets and Ustinovskiy, which we posted relatively recently on the archive. And I will refer to that work as ASU. That's, we saw many great papers by Nigel, very important papers, and I will show you one that I think didn't see so far. So this is a paper about Poisson structures and generalized Kahler geometry. So the relevance of this paper is essentially the last line of the abstract. So Nigel highlighted the role of holomorphic Poisson structures in relation with bi-permission generalized Kahler geometry. But this particular paper is of significant importance for me because it somehow reminded me my time at Oxford as a postdoc. Nigel invited me to speak to the seminar, and after the seminar, he invited me to discuss in his office, as he usually does. And at that time, the problem I talked about at the seminar, and I spoke with him, was actually the construction of bi-permission structures on CP2, and I didn't know how to do it. And the reason we were interested back then in this situation was a joint project with Gilbert Chow and Paul Buduchon, and we wanted to understand four-dimensional manifolds for which the Weyl tensor determines a maximum number of integrable complex structures. And we had some examples, but they were kind of as a K-tree synthesis story, and we would not know how to treat a manifold like CP2, for instance. And of course, Nigel, in this beautiful paper, shows a deep connection, and of course, he constructed such structures. So anyway, let's now get back to the main subject of the talk. It will be essentially motivated by a situation we know in the classical Kahler case, the so-called Calabi problem. So I will briefly review the Calabi problem in the Kahler case, and this motivated, I will tell you what we can do with the generalized case. So we start with a compact complex manifold, and I just remind you that the Kahler structure or Kahler metric is defined in terms of a closed two-form on that complex manifold, which is of type 1,1, which agrees with the complex structure and which defines a positive definite metric. So it's a type 1,1 positive definite. And such a form, of course, gives rise to a deRham class being closed and being also symplectic because of the positive definiteness. And what one could consider is actually the space, the moduli space of all Kahler metrics with the property that the Kahler form belongs to a fixed deRham class. So this sometimes is called the Kahler class of metrics. Now, the key feature in this classical setting is that if we fix one element in this space K alpha, then because of the Debye-Bar lemma, you can actually parameterize all other elements by smooth functions modulo constants. So in a little bit more fancy way, you can think of this K alpha as a Fréchet space. It's kind of open in the C infinity topology. And you can in particular define the tangent space by using this Debye-Bar lemma. And the tangent space, of course, is a copy of C infinity. So it's kind of a situation where you have an infinite dimensional structure of a manifold on this space of relevant structures. And this point of view actually piqued the attention of Calabi, who wanted to extend the Poincare uniformization theorem to arbitrary Kahler manifolds. And in the 50s, Calabi asked the question whether or not we can find a special representative of this K alpha. And so he talked about canonical, and for him, canonical was a Kahler metric whose scalar characteristics. And actually, he even conjectured that if the manifold doesn't have automorphisms, such an object exists in infinity. And the point that Calabi made available in his initial contribution was actually that's a problem about solving a PDE. And you can see it from the description of K alpha. So we want to solve scalar curvature equal to constant. You could actually observe that this constant is topological constant. We know it in advance. So what we really have to do is to fix a omega 0 at a base point, and then look for smooth function such that the deformation you get satisfies the next scalar omega equals to constant to that constant, and that's clearly the fourth order PDE. However, that's not an easy PDE to solve. And it has occupied the community for several centuries. And today we have kind of a clean conjecture, at least, which says that you can find such a metric if and only if the initial manifold is what's called uniform case stable. I'm not going in details to these definitions, but the idea is that this uniform case stability is a complex analytic condition. It doesn't depend on any metric. So I listed some cases that have been known. So the initial Calabi work initiated subsequent work by Yao and Ban, and they were able to show existence of such metrics in the case when the underlying manifold has vanishing Furtian class, the seven famous metrics. As well as in the case when the canonical bundle is ample. These are the famous Kahler-Einstein metrics, negative Kahler-Einstein metrics. But the problem took much longer time to be settled in the final case, in the Kahler-Einstein, positive Kahler-Einstein case. And that has been achieved 2015 by work of Chen and Donaldson Sonic. And we now have various recent proofs of the same result. So this type of conjecture now is true at least for final manifolds, but also even more recently, it has been settled for arbitrary Kahler classes on toric, on smooth toric varieties. So those are compactification of the equivariant compactification of C star. And in this case, actually, what happened is that the PDE, the analytical problem, if you want, led to this notion of uniform case stability. It appeared as a slope of some function that governs the existence of the solution. And this case stability, in turn, allowed one to actually define moduli spaces of Kahler-Einstein. This was completely successful for this development. And there are now progress made to do this for arbitrary polarities. So this is an instance where somehow the right analytical problem leads to the definition of the right stability condition. Okay, so that's my kind of a brief survey of the situation in the Kahler case. Now I'll move to the situation that I would be interested in for the remainder of the talk. And this is a situation where we fix an extra holomorphic object, extra structure, which will be a holomorphic Poisson tensor. So just to remind you, a holomorphic Poisson tensor is a holomorphic section of the bundle of two vectors over your complex manifold, whose scalping bracket itself is 0. I just here put you the definition of the scalping bracket, the extension of the bracket to two vectors. And you could think of these Poisson structures on a given complex manifold as algebraic subsets in the finite dimensional vector space of holomorphic two values. So in some way, what we'll be doing is kind of a reminiscent of what happens with this Higgs bundle. So you instead of having just a Kahler manifold, you add an additional structure, which will be this setting holomorphic Poisson concept. Okay, so here are some kind of basic examples of Poisson manifolds in complex dimension 2. The starting bracket condition is trivial, so Poisson structures are just sections of the anti-canonical bundle. We have abundance of examples. For instance, Delpetro surfaces have such sections. And another example, which will be relevant for the last part of the talk, is toric variety. For toric variety, we can take the generators of S1 in each of the C-star factors. We can fix two skew-symmetric matrices, A and B, and we can consider this kind of two-vector, which clearly will Poisson commute because these are generators of the toric. So these are toric Poisson structures. And another much studied case is to take a holomorphic symplectic manifold. So this is a complex manifold endowed with a holomorphic closed 2-0 form, which is everywhere non-degenerate, in which case we can invert this 2-0 form to create a vector and this two-vector plus. So these are kind of typical examples of Poisson manifolds. So the problem here is to define geometric structure, differential geometric structure, for instance, Hermitian structure, which somehow is adapted, which sees this Poisson tensor. And this is not kind of an obvious problem, because if you want something like to have a connection which preserves the Poisson tensor, it is not going to work in cases where this Poisson tensor has non-trivial zero values. So you have to do something more clever to find such structures. And it turns out that the structures that will work for us are what I would call symplectic type generalized structures. We saw in Marco's talk this morning what is a generalized scalar structure. If you get two definitions, I will use one of those, first definition. So here's the definition. So we start with a complex manifold and a generalized. So this complex structure will be fixed to complex. So we fix the complex structure, and we pick up again in a closed 2 form. And instead of being of type 1-1 to be compatible, we will just require that the 1-1 part of this 2 form is positive definite. Or this is equivalent to say that if we twist omega by J and take the symmetric part, it's defined as a metric. So in symplectic geometry, such situation is known as omega times complex structure. That's the data. So far we are kind of a more general than Kahler situation. However, we now impose a third condition, which is kind of an important condition. So given omega and J, I can actually define another Balanced complex structure by conjugation with omega. And what I would insist as an additional condition is that the second Balanced complex structure is also integrable. For instance, if this omega was already Kahler of type 1-1, if I do this conjugation on the third line there, I will get again J. So it will be mathematically integrable. So that's the familiar Kahler situation. And the point perhaps here is that this Riemannian metric that is defined on the second item will be compatible with both J and I. So we covered this factor integration at this point. Okay, so that's the formal definition and how it's relevant to Poisson geometry. Now, starting with this generalized scalar symplectic type structure, this essentially 2 form omega, we have a bunch of tensors, of course. So we already introduced the second integrable complex structure. we introduce the Riemannian metric, and in the Riemann algebra will show you that I and J will be orthogonal with respect to this Riemannian metric. And then you can take kind of a commutator of I and J and act with the metric -1. And what you're going to obtain is a smooth two vector. And this smooth two vector can be turned to a complex two vector by just taking the type. And here is the contribution of Nigel in that paper that I show you. Actually, you observe that this pi omega, this two vector, the real two vector is the real Poisson structure, and the complex two vector is a holomorphic Poisson. So this you could also think as an obstruction to the existence of such a structure, present in manifold general type would not have Poisson tensors, and therefore this generalized scalar structures of symplectic type will go together. But on a Poisson manifold, we can ask whether the Poisson tensor can be realized by such a structure, so generalized scalar structure of symplectic type. And here is another important construction Hitchin did just after the first paper, and this construction has been further generalized by Goto and Gualtieri. I think that the theorem I state here is from Gualtieri 2018. Essentially, it tells you that if you have a Kahler background and Kahler manifold to start with, which has a some Poisson holomorphic Poisson structure by G, then you can always find a generalized scalar structure on that manifold for which the corresponding tensor is like G. Essentially, to any Poisson tensor, Poisson manifold, we can associate a generalized scalar structure of that type. That's the key point of the whole talk. Okay, so any questions about that? Okay, so now I will kind of make a new setup and will convince you afterwards that it's something worth considering. So we start with a symplectic type generalized scalar structure. Let's say when is 0. We'll fix the deRham class of this structure, and we'll consider the moduli space of all symplectic type generalized scalar structure in that deRham class, for which the holomorphic Poisson tensor is the given. By construction, we have at least one element, and we want to know what are the other such generalized scalar structures. So that's the naive proposal. Of course, just as a preliminary remark, if we take this Poisson structure pi j to be 0, then you can see that necessarily the compatibility will tell us that the generalized scalar structure must be Kahler, and we rediscover the class Calabi. So this is kind of formal generalization, but there are various problems that you immediately want to address. So the first problem that we want to address is to make sure already that this space is it doesn't reduce to a single point, for instance. So what is the structure of the space? Is it path connected? Is it contractible? Can we really have something like the space carried out before, which is modeled on smooth functions? And if you want to extend the Calabi problem, we have to also know what will the substitute of constant scalar quadratic element in that context. So these are the two problems that I will discuss in the talk from now on. Okay. So I'll start with the first problem. So what one can do is there is so Marco Gualtieri wrote a generalized scalar Hodge decomposition. So this happens on the generalized tangent on P plus T star. But using that, you're working with generalized scalar structures of symplectic type. You could obtain from that generalized scalar Hodge decomposition some sort of a classical Diding-Bauer. So So what that says is that if you have a symplectic type generalized scalar manifold, and you have an exact 1-1 form with respect to I, with respect to J, that would be the same, then this exact 1-1 form is a DD bar of a function. So these generalized scalar manifolds, they share some features of Kahler manifolds, in particular that level is true. So because of that, if I take a path, if I suppose that you have a smooth path of representatives in your object, in your generalized scalar class, then the compatibility condition actually will tell you that the derivative of this family of symplectic forms must be of type 1 with respect to the moving structure IP, just by compatibility. And since we are in a fixed deRham class, remember, this will be exact, and then therefore we can write the PD bar of a function which I called phi dot t. So this tells you that at least formally, the tangent space of this general scalar class is indeed C infinity functions modulo constant, and I will kind of normalize the situation. I will really think of this tangent space as C infinity functions normalized to have 0 mean with respect to the basis of the measure. This will be the tangent space. And of course, at this point, we ask, well, that's formal. I don't even know if one such path existed. And here is another kind of really important construction from Nigel Hitchin's 2007 paper, which was actually generalized, extended by Marco at 2 occasions, I think, at the 2 birthday conferences of Nigel. But at the end of the day, we have this very beautiful statement, which tells us the following thing. So that essentially, I will build an exponential map from the samples to my space of informations. So you take a time-dependent function, and with this time-dependent function, you can construct a time-dependent vector field using the real part of the holomorphic Poisson test. This is a real Poisson. So this is kind of a Hamiltonian vector field in Poisson geometry. With this time-dependent vector field, you consider the isotopy of your method. And what you have to do as a preliminary work is to deform the initial I structure with this deformable. So you get a one-parameter family complex. And then the miracle happens is what essentially Marco showed, is that if we deform the initial structure by omega t plus this integral 0 to t minus 1 drs t bar rs p dot s ds, then for small t, this deformation will give you a path in the space jk pj alpha. And of course, this path will satisfy the defining equation for as before. And the miraculous thing is that actually the conjugated I structure would be the one that makes it defined. Very neat. So for instance, if you do this for 0 Poisson terms, let's just look at the model. Then Vt, of course, will be 0. This diffeomorphism will be the identity. So this RT will not move, and you get the information. So this tells you that this space of general scalar classes is kind of a reasonable space to look at. And the way I want to think about it is as a formal Friesian manifold, because the tangent space will be just this normalized function, and the advantage of this description is that we have a natural formal remaining, because I have to know about these functions. And having spent some time on the side of Kahler geometry, I knew this beautiful work of Noguchi, who did the same thing in the usual Kahler setting, and he, in particular, computed the remaining curvature of this formal Riemannian structure, but we found exactly this beautiful formula in A. So the same formula holds in the general scalar context. In particular, you see that the sectional curvature is non-positive. And the second thing you can do, you can even go on and write the geodesic equation in this formal Riemannian structure. And it turns out that in this case, it's a straightforward situation of what we already knew in the Kahler case. So you see the last one is the geodesic equation for curve. And in the Kahler case, of course, J is equal to IT. So the second term on the right-hand side is equal to the first. So we get a familiar geodesic equation. So this theory very beautifully extends to this general scalar set. Okay, so now the second problem: how to define scalar code. Okay, so that is a problem that brings me back to the subject, really. And the reason is this conference. This is a conference in Bath in 2010. You can see familiar faces. The most important is to see Nigel up there, right? See. So this was a conference in general scalar geometry, organized, I think, by Marco and others that we attended. And this also was a conference when this volcano erupted in Ireland. So we have been stuck there for some time, actually. And being stuck for some time, actually, we profited the beautiful surroundings. So this is a work that we did with I think, Jacques Tobis, Nigel, and Paul and myself around this beautiful lake piece. And at that point, I think Nigel asked me and Paul what would be the scalar setting. And with Paul, we get very excited because we had a clue how to answer the question. So the clue is here. So what we knew is that we can switch gears temporarily. This is familiar for those doing Kahler geometry by observations by Fujik and Donaldson. So what we do now, we fix a symplectic form like 0. And we forgot about integrability completely. And we consider almost complex structures which are obtained by this fixed symplectic. So this is infinite dimensional formal manifold. And we knew how to define a formal Kahler structure. And now we have the group of Hamiltonian morphism, which acts clearly on that space. And what happens is that in this picture, you can also consider the space of compatible. So AK omega 0 will be those which are compatible. Times confidence difference omega 0 compatible. So this, of course, is a subspace in this bigger space, which, as I said, is formally Kahler. And this embedding actually is in the formal embedding of Kahler manifold. And Fujik and Donaldson knew that if you act with the group of Hamiltonian transformation, this action preserves the subspace. The moment marks the scalar code. So we talked with Paul. Well, it's enough to find what is the momentum map of this action in this bigger space, and this will be our generalization. Unfortunately, we tried for a year without much success. The problem is that the formula were too messy. We could not really find those formulae. And we gave up, and I gave this problem to a PhD student, Boulanger, in 2019, but I asked him to consider the toric case. The toric case, there are some significant simplifications, as we'll see in a moment. And Boulanger actually found that this action is Hamiltonian, and he found this formula for the formula on the second line. He confirmed this formula in dimension 4. So he found this formula for toric coordination. So the moment map is the scalar curvature of this big region metric plus some kind of a Laplacian of size 1 over 2 logarithm of the ratio of the volume form volume form. And this additional term of dB is so minus omega g, the symmetric part is a metric, and that symmetric part is a form. So when you take dB, you get a 3 form. This is the H form from Marcus. So he found this beautiful formula, but then Goto came in, and he actually proved that without any toric assumption, this action actually is Hamiltonian. The problem was that Goto used formalism of spinors and generalized Kahler structures on P plus discovered. It was not clear that the formula he got has anything to do with the bidimensional data. So we had to work recently to show that Boulanger's outcome agrees with Goto's inclusion. So that's the answer. So what I would propose that we take this expression as a definition of generalized curvature. So let's do that. Now we define analog of Kahler class in analog of generalized scalar curvature. We'll be asking to find a representative, a generalized scalar curvature, and that's generalized Kahler class for which the scalar curvature is constant. But we do have now a GIT setting. So there is a last test to see what we are doing in science, and that's the dilemma that we're seeing upstairs. So we have two objects now. We have this generalized Kahler class where we fix the complex structure and RAM class, and we have this GIT when we fix the symplectic. We can relate these two objects by Moser. So if I have a path of symplectic form standing fixed complex structure, this is symplectic isotopy. So we can use such Moser lemma to send the path of generalized Kahler structure in the class to a path of complex structure in the AJ omega 0. And if you compute carefully the velocity, you will find out that what you get in the GIT side lies actually in the form of complexified transformation, and it's actually transversal to the time space above. So this means that the problem I propose you is equivalent with the problem of finding zeros of the momentum map in the complexified form. So that's kind of a convincing point that what we are doing is plausible. Okay. So now the advantage of this GIT is that it gives you a toolkit of features. So here is one feature that I want to emphasize today. So these are ideas that have been pushed in the Kahler setting by Noguchi. In particular, just using the Moser trick as before, you can see that now on this generalized Kahler class, you have a closed one form. This is essentially the moment map that you push it back on the complexified orbit, and you consider it there, and this will be closed. So the GIT picture gives you without any work that this one form on your Frischmann manifold from JK out there will be a closed one. In the Kahler case, the Kahler class is absolutely tractable space, so this one form will integrate, and that's how the Noguchi energy was introduced by Noguchi. In our case, unfortunately, we don't know whether or not this space is contractible, so maybe it's not always possible to integrate this one form. But even if you don't integrate the one form, there are already consequences of observations we had before. So here is another generalization from ideas from Kahler geometry. You can check actually that this one form is monotone along geodesics. So we find a notion of geodesics, so smooth geodesics, if they exist. This one form stays monotone. In Kahler geometry, this corresponds to the fact that the Noguchi energy is convex. You can integrate, you can find a primitive of this one form, and the corresponding function will be convex. Also, this one form, it vanishes by definition if and only if the general scale code is constant by the very definition. So as you see, if we could find a primitive, the functional we will get will have as critical points this generalized Kahler structure of constant generalized scale curvature, and this convexity suggests a uniqueness. I will show you actually how all this kind of general picture works in the case of toric Poisson. So here's the last part of my talk. So we consider the toric case. In the toric case, we have a toric manifold, Kahler toric manifold. You take a toric Poisson tensor, and I denote by T the real. So our result in this situation is that first we can reduce the problem to T invariant generalized. So zero. Then we can prove uniqueness using this convexity property. And moreover, we can actually, in this case, essentially completely understand obstructions in the sense that if we have a constant star approach to general scalar metric, which is invariant, then what we can show is that the Polytop has this property known as uniform reducibility. And by these recent works that I quoted in the beginning of the talk, we can actually conclude that there exists a element in that same class, which is a constant star approach. And then we can use perturbative methods to obtain generalized scalar metrics of constant scalar generalized scalar curvature, but for small multiples of the Poisson tensor. So to get an optimal result, I would like to take T to, but for the moment that's not possible. So I will go very quickly through the elements to show just how it works. So the reduction part is also kind of a piece of general consequence from the GIP picture. It uses the so-called Nishnirovich-Matsushina abstraction theory. So what it tells you, that's completely in a general situation. If you have a constant scalar curvature general scalar metric, then we can show that the isometric object, when you complexify it, you get the full symmetry of the Poisson manifold. These days, there are formal proofs of this fact from the GIP explanation that applies in our case. So in a toric situation, these are simply connected, so we don't have H10 code. So this bonds down to this reduced holomorphism group will be the whole. So on a toric manifold, what I will have is that the connected component of the holomorphism group of the Poisson structure will be down. Okay. And in particular, it will contain the maximum norm. So in particular, I can conclude that any constant scalar curvature, generalized constant scalar curvature metric in that situation is invariant up to conjugation. Uniqueness. Now for uniqueness, I will use the convexity of this Mabuchi. By the way, in this case, Mabuchi energy does exist, but I will use this result we have shown before, that if I manage to show that the situation is geodesically convex, which 2 points can be joined by a smooth geodesic, then I can use the arguments before to say that actually any 2 critical points are isometric to each other. So how that works? So it goes to the description of this generalized scalar structure in the toric situation. This is this theorem is taken from the thesis of Boulanger and certainly by Wong. So the point here is that in toric Kahler manifolds are described in terms of those polygons. I will fix the before the Poisson tensor, which is given by two skew-symmetric matrices. Their theorem says that the generalized Kahler structure of symplectic type are defined in terms of a convex real function U defined on the interior of the polygon, and which satisfies certain strong convexity conditions. So what is the convexity condition? You take the Hessian of this function, you take imaginary part, the matrix B, so this is a Hermitian object. And you want this to be positive in the interior of any face, including in the interior of the polygon. And if B was 0, this is the familiar Abreu-Gilman description of toric matrix. What's important for us is that this convexity condition is stronger than the Abreu-Gilman condition. In particular, any element, any omega will define a genuine parametric given by the U. And you see how it goes. So the symplectic form of omega will be the so-called standard value, omega 0, which I noted. And you deform it by BIG, the mu so this stays symplectic form because the top power will be the same as omega 0, so it's still a symplectic form. It's deformed by this constant magnitude in that way. And there is another type of deformation. You can do this time on the level of the complex structure. In a standard Abreu-Gilman situation, the corresponding complex structure will be given by the Hessian of this U. Whereas in this case, will be the Hessian of U plus this second matrix A. And if you want to describe the I structure, you have to essentially replace A by minus A. So some kind of B has a distinguished role, and J and I roll one to the other by replacing the matrix I A by minus A. So that's a very beautiful description, but what it means to us, it means that we have actually two descriptions. If I have a path of generalized Kahler structure, I will have the corresponding convex functions U, and I will have these velocity functions here. And the important point is to understand how they are related. And what happens here is the usual miracle in this type of questions is that actually this minus phi delta, this potential of the velocity is actually the derivative. So you don't use any diffeomorphisms anymore. You get a complete description in these terms, and the Julisk equation, most strikingly, is just a strike segments of functions. So this proves you that in the toric case, you are geodesically convex, and therefore the space actually is contractible. And by this conditional uniqueness, we can show the uniqueness. So the interesting part of real cycle. Oh, okay. So now, so now I want to discuss probably the most interesting part of the proof is the abstraction. Right. So if you in this paper of Boulanger, actually, in one step, they actually found the moment map, and the moment map is given by the expression in terms of Hessian of U at the median. So the question of the problem of finding toric metric of constant generalized Kahler curvature reduces now to a genuine PDE because of this interpretation in terms of U. It's not an easy PDE to solve, of course. When B is equal to 0, that's the famous of real equation. But fortunately for us, this equation has been much studied in theory of Kahler metrics of constant Kahler curvature. So the important observation is the following for us. So that's the kind of key element that leads to the solution. So this Hessian of U plus imaginary part B, this is a Hermitian symmetric matrix, and the conditions for the structure to be globally defined is that this is positive element in the interior of each case. Because of that, the inverse will be also a positive definite recognition matrix in the real part, which I denote by X, will be a positive definite matrix. So I can use this positive definite matrix to define another t-invariant metric, which I call by G bar. So this G bar is a different metric than that back emission metric theory. And this G bar metric will be not, so it will be actually compatible with the standard with omega 0 selected for. And it's not going to be a Kahler, it will be just Arnold scalar. Or expression of Arnold scalar. So it will, with respect to omega 0, it will give rise to another Arnold complex factor which is not integral, which is not related to this factor before. But the important thing is that this object will be globally defined. Key argument here is to see that the boundary conditions that your initial metric will satisfy are enough to induce that this new metric, which I define essentially over the preimage of the theory of the polygon, is globally defined. So we have a toric scalar metric, and the expression in the PD there just means that this matrix xig satisfies xig. The limit with respect to I, the limit with respect to J, sum is constant. And what this sum calculates actually is the scalar curvature of the Arnold scalar metric with respect to the remission. So this is an Arnold scalar metric of constant remission sum. Now, with this discovery, what we do, we go through the theory that Donaldson developed in the usual case. So in the Donaldson theory, he considers constant scalar curvature elements. But the big view of this theory also holds true for Arnold scalar, exactly in the form that we just found. So in particular, we can see that this constant is kind of a predictorial topological constant given by the ratio of the polygon of the boundary of the polytop against the volume of the polytop. You can see that if you have a solution because of this positive definiteness of the matrix, you have some sort of a key inequality, so this two-star property. It says that if I take a continuous convex function over the polytop, which I normalize to vanish at a given point, to vanish at that point, it will be minimal at that point, so I kill that. You have a kind of a priori inequality between the L1 norm of the function and the integral over the boundary. So this is the familiar condition that Donaldson called uniform case stability over the polygon. And you can also take in this inequality piecewise linear functions. So those who respond to the derived objects, if they are rationally piecewise linear function, you can see them as kind of a roof building on top of your polytop. So this describes what's called test configuration. And since it's sufficient to test such type of inequalities on such functions, actually, as was observed by Goto and this condition is equivalent to the algebraic condition of uniform case. I'm not going to define exactly what it means, but analytically, if you want, in terms of the polygon, uniform case stability means exactly this a priori inequality to all normalized complex continuous functions. So we have it from just following what was done in the Kahler case. So with that outcome, it comes the existence test, fourth step of the theorem, how it was the existence results. So the whole point is that this Chen result, which builds on Shu and Shu, they literally show that if this this a priori estimate holds, then you can find a constant scalar curvature. So we have a constant scalar curvature metric in the deRham. And what we do now is we want to set up a perturbation problem. So we will do a kind of a perturbation problem implementing this in the equation. So we have a solution of equal to 0 for this solution corresponding to the constant scalar curvature toric metric. and you want to find some solution for T of 1 in real T. Now, the convexity conditions or the functional spaces a priori depend on B, but they all belong to the convexity condition for B equal to 0. So we can work on that common space and apply implicit solution to show that actually you can find a solution at least for small B. So that's essentially the argument we did. So to finish, let's just discuss some questions. There are many other questions that I can discuss, but there are a few questions that I want to mention, briefly say something. So we don't know as of yet what are the topological properties of this space of generalized scalar classes. So are they connected? Are they contractible? We don't know that. But we do know something in the symplectic holomorphification. Probably Jeff will mention this in his talk tomorrow. What we can prove, for instance, in that case, is that if you consider the hypercalabi, then actually the connected component of this hypercalabi inside this space is defined is contractible. So what will happen there is that so-called generalized Calabi flow will contract a given element to this hypercalabi in a given way. So that's why this is true. Another question which I'd like very much to have some more clear idea about is whether we can really define a K energy or Noguchi energy in general. In this toric case that I just discussed, this is possible. We have a close formula for that. And it's also possible to do this in the holomorphics. Also, this not always in general. We don't have this in general. And of course, you could even play with some basic questions. So what about looking at CP2 and see how this existence problem presents itself? So our result that I just presented, the toric existence, tells us that if you take 3 lines in general position, then in this case, also the Poisson tensors are sections of all 3. So you take 3 lines in general position, then you get solutions. You get generalized Kahler matrix of generalized Kahler scalar curvature constant. But you can also consider another case, for instance, 3 lines which intersect in a point. You can see that the morphism group is not reductive, so you know that in this case there are none. But you can also consider, for instance, smooth elliptic curves. So we discussed with Baron yesterday over evening, over dinner, that this is a very interesting case. We have no clue. Here the morphism group is sphere. So you would think that probably there are no obstructions coming from Hitchin-Rogic theorem, and then therefore the only way probably to attack this problem is to define the proper notion for Poisson case stability and to see in this case the situation is stable or not. So I will stop here. Thank you.